Yes, questions? A plate? A plate? Okay. No, it was a loop. Okay, the magnetic dipoles. Let's just go over what we had done on last Thursday. We started studying the magnetic field. We said that the magnetic field exerts a force on charges, and the force that the magnetic field exerts will be given by, it is proportional to the charge. Okay, it is proportional to the charge. It is also proportional to the speed of the object and also to the magnetic field. But it also had this property that it was also proportional to the angle between the two, and it was always perpendicular to both the velocity and the magnetic field. This was basically our definition of the magnetic field. So this was how we had defined the magnetic field, actually. By measuring the force for different velocities, we could determine the magnetic field at a given point. And then we said that, okay, if the force, the magnetic field exerts a force on moving charges, we had also studied the current, and we know that the currents are nothing but moving charges. So the magnetic field should also exert a force on current-carrying wire. And if we had a wire of an arbitrary shape, and that is carrying some current I, and you can just consider a very small segment of this wire and define a vector dl. Now the length of this dl is equal to the segment that you are considering, and its direction is along this segment and pointing in the direction of the current. So the force acting on that segment, if we just denote it by dF, this is the force acting only on this segment. And let's say the magnetic field is pointing downward in that region. This was proportional to the magnetic field, to the current, and also to the magnetic field and the length that we considered. So this was the relation between the force acting on this very small segment, dl, I, and B. So for this configuration, what would be the direction of this force? So this is our dl. This is B. So I just imagine this rotation of dl towards B. So this is the direction of the force. It is perpendicular to this length dl and also to the magnetic field. So this is the direction of df. Okay, so after this point, we already know what the magnetic field, what the force acting on a wire is. We can just apply it to a system. We imagine the loop, not a plate, but it was just a current-carrying loop. So it's just something like this. Well, in fact, we can consider an arbitrary shape, but just for simplicity, we consider the rectangular loop placed inside a magnetic field. So let's say it is carrying a current in this direction. This side has a length A, and this side had length B. And we also imagine that there is a region of space which has a uniform magnetic field. And we place this loop in this magnetic field with some angle. Let's say this is the angle, assuming we are just looking straight from the edge. This is the side that has length B. And the current, we place it here in such a way that the current at the top part is going into the screen, and the current from the bottom is going out of the screen. So if you just imagine, this is a rectangle of this shape, and the current is just running like this. So this is a three-dimensional object. There is depth to this picture. I use my keyboard to visualize it. The wire is just the boundary of my keyboard. So I just place it like this, and the current is running, from my perspective at this point, it's running in the clockwise sense. Then we started what are the forces acting on various parts. There are 4 segments of my wire. What are the forces acting on each part? There is the top part. Well, in the top part, the current is going into the screen. Magnetic field is in this direction. Remember, dF is I times dl cross P. dl is into the screen. B is in that direction. So dl cross P, just use your right hand, it is pointing downward. So the force acting on the top is pointing downward. Let's say this is F1. And the magnitude of F1 is equal to I times A times B. Basically because we don't need to integrate this, because the dl is constant along this segment. B is constant along that segment. So basically, if you just sum the forces acting on each part, it's just I, which is constant, B, which is constant, times the length of that segment, which is constant. Well, the angle between dl and B, what's the angle? 90 degrees, because B is pointing in that direction. dl is into the screen, so there's 90 degrees over here. So this is the magnitude of the force. Now let's look at F2. This is the force acting at the bottom. Now dl is pointing out of the screen. The current is running towards you. Magnetic field is still in this direction. So dl cross B, it is pointing upward. And the magnitude of F2 is also the same. It has the same length. The magnetic field here the magnetic field is constant, it's uniform, so the magnetic field is the same, current is the same. So you see that F1 and F2, they point in opposite direction. One is pointing straight up, the other one is pointing straight down. They have equal magnitudes, so if you just sum them, the net vertical force acting on my system would be 0. But this is only true because the magnetic field here and magnetic field there are the same. So if the magnetic field is not uniform, then the net force will not be 0, and you can basically calculate the net force. That was the one of the questions in your homework. True, if the net force is not 0, we know from Newton's dynamics that there should be the system should be accelerating unless there is some other force acting on the system, which will cause the net force to be 0. Now let's look at this edge and the other edge, the 2 edges. Let's look at the closer edge. In the closer edge, the current is running in this direction. This is the direction of I. This is the direction of dl. This is the magnetic field. So the force will be in which direction? It's into the screen. This is my dl. Because you see, the current is running like this. I'm calculating the force acting on this edge. On this edge, this is the direction of the current. This is the direction of B. And the cross product is into the screen. Or if you let me show it in this other graph, the force acting, let's say this is the outer side. This is the direction of the force. Let's call it F3. Now if you look at the other side, the further away side, that side, again remember the current is running like this. So at the further side, the current is running in this direction. This is the direction of I. This is the direction of B. I cross B is out of the screen. So this is the direction of F4. And again, F3 plus F4 will be equal to 0 if the magnetic field is uniform. You see, the force depends on the magnetic field, I, and the length. This side and this side has the same length. They both have the same direction of dl. Well, just opposite directions. That's why they have the opposite directions and the same B. So if this is satisfied, if B is the same, then these two forces will exactly cancel. If B is different, then of course there will also be a net force in this direction. So basically we have these four forces, and all of those forces, they sum up to give 0. But still there will be some torque acting on my system with respect to the center of mass, let's say. Both of these forces, F3 and F4, they pass through the center of mass, so they don't create a torque. But nevertheless, F1 and F2, they don't pass through the center of mass of my rectangle, so they will create a net force. And if you remember the definition of the torque we had defined as R, which is the vector pointing to the location where the force is acting, and cross F. Let's say if there are more than one forces, you just calculate the torque of each force and sum them up. And now what we did was, for each one of these forces, we calculated the torque. This is my center. This length is B over 2. This length is also B over 2. Let's call this angle to be theta. That angle between the force and my rectangle. Then the torque created by these forces, what are their direction? Well, you see, there are two forces. There is this force, F1. This is my R. R cross F. R, F. R cross F1 is into the screen. If you do the same for F2, this is R. This is F2. R cross F2 again into the screen. Both of them create a torque into the screen. Both of them are trying to rotate my rectangle in the clockwise sense. And if we identify the into the screen as my z-axis, the net torque will be just, let's see, the torque of the F1 will be, well, the distance is B over 2. The magnitude of the F1 is I times A times B. And the angle between the two, the angle between this vector and the F vector, the force vector. You see, this is theta. So this angle over here is pi minus theta. So the angle between the position vector of this point, where F1 is acting, and F1 is pi minus theta. From the definition of the cross product, so we have the sine of pi minus theta. This is the torque due to F1. It's all in the z direction. Let's call it torque 1. And now we have the same thing for the second force. We already said that it is in the z direction. So let's calculate the magnitude. It's again B over 2. This is the length of R. Times the magnitude of the force, which is again I times A times B. And then sine of the angle between R and the force. And that is also pi minus theta. Now, if we just combine, this is due to force 2. Now, if you just combine them, the total torque acting on my system is just in the z direction Well, both of these terms are in fact the same. Both forces contribute the same to my torque. This is equal to I times AB times B times sine of pi minus theta. So this is the torque acting on this rectangular loop circuit due to the magnetic field. Now we would like to write this in terms of some vectors. We already know that B is the magnitude of a vector. There is the sine of an angle which just resembles the vector product. We only need to identify I times AB with the magnitude of another vector. And that vector is what we call the magnetic dipole moment. We say that we define a vector. You see, this is our torque expression. Now we define a vector we call the mu vector, whose magnitude is I times AB, or I times the area. AB is just the area of this rectangular loop. And in fact, it turns out that you can do a similar analysis for any loop of any shape. The torque expression will look like this. We will be defining the magnetic dipole moment in a moment, but the magnitude of this magnetic dipole moment will always be the current running through my loop times the area enclosed by my loop, whatever the shape is. Well, we have to identify its direction also, this mu vector. Now, the way we do it is, okay, this is my loop, and we said that this is how the current is running in my loop. So I just take my right hand, curl it in the direction of the current, and then my thumb points in the direction of the magnetic dipole moment. So this is the direction of the magnetic dipole moment. Now you see pi minus theta is also this angle over here. This is the direction of B. This is the angle pi minus theta. So this is my mu. This is my magnetic field. This angle is also pi minus theta. And furthermore, if you just take the cross product of mu and the magnetic field, you obtain a vector into the screen. So this torque expression that we obtain, we can write as mu cross B. If you just look at this vector over here, its magnitude is the magnitude of B, which is I times AB, the magnitude of B, which is B, times the angle, the sine of the angle between these two, but the angle between those two is nothing but pi minus theta. This angle is just pi minus theta. So the magnitude of this vector and this vector, they are the same. Furthermore, if you just consider the signs and use the right-hand rule to determine the direction of mu cross B, it is mu cross B, it is into the screen. So this vector and this vector, they are pointing in the same direction and they have the same magnitude. So they have to be equal vectors. So this is our magnetic dipole moment. Good point. Mu vector is equal to I times the area vector. Okay, let me answer your first question. Well, let me start with your second question, which is the easier one. Before answering that question, though, how do we create a magnetic field? So we will be studying how we create a magnetic field this week. And then we will also discuss how we can create a uniform or almost uniform magnetic field. we will see that we can create an almost uniform magnetic field just like almost uniform electric field. In the case of the electric field, we said that if we have parallel plates sufficiently large, very close to each other, in that case, the electric field in between will be almost uniform. We will see that there is an analog in magnetic field. We can create a system which has an almost uniform magnetic field. Now let's come to the first question. Why does the magnetic force only affect moving charges? Well, why does the electric field affect charges? We don't know. So we don't really know why there is an electromagnetic force at all. Well, it is nice that we have them. That is how the atoms can form and how we can exist. But why in the universe do we have magnetic forces? We don't have an answer for that. But we know that there is an electromagnetic force, and it's, in a sense, it's just the terminology. We have this electromagnetic force. We know that that force has a part that depends on the velocity and has a part that doesn't depend on the velocity. The force the component of the total electromagnetic force acting on a charge that doesn't depend on the velocity is what we call the electric field. And the part that depends on the velocity is what we call the magnetic field. So it just appears that there is this force to start with, and there is one part of this force which doesn't change as we change the velocity of the object, and there is another part which changes as we change the velocity of the object. And the part that is changing as the velocity changes is what we call the magnetic force. Other questions? True.
And we know that while moving the charge from there to there to this room, there is induced magnetic field, right? After there is a magnetic field from the current from the charges moving in this room, and there is an outside magnetic field also.
Yeah. Okay. We didn't yet discuss what is the magnetic field created by this current. So just don't forget your question. Ask it tomorrow, after we discuss how the currents create a magnetic field.
Can we create an analogy like that? We have a charge and it is the electric field like it's the surface and there is a charge on it. So when it moves, while it's moving, it's creating curvature like gravity of creating.
Okay. What is curvature? What is gravity, etc. Well, okay, there are people who are treating this force, this electromagnetic force, as the curvature in gravity. But let's discuss it in the break.
Why is it that magnets sort of have a constant magnetic field, but for a charge it has to be moving in order for a magnetic field to be created?
Let's solve an example. Well, let me also ask another question. I will not discuss it in more detail. But we had discussed Galilean relativity in mechanics, right? So the physics laws should be independent of reference frame. At least the acceleration should be independent of the reference frame. If an object is accelerating in one inertial reference frame, it should be accelerating in every inertial reference frame, right? So let's assume that there is a magnetic field over here in this region, and there is a charge moving in that direction. So it will be feeling this force. There will be a magnetic force acting on the object, right? Now let's suppose that I started moving with the charge. I go to another inertial reference frame which is moving with this velocity v. Well, in that reference frame, the charge is not moving, right? Because I'm also moving with it. If its speed is 0, there is no magnetic force acting on it. But its acceleration should be the same. It should be accelerating. So what causes the acceleration in that frame? No, we are not. Just look at this one. At a given instant, I'm just looking at one instant. My charge has a velocity in that direction. In this reference frame, let's say the magnetic field is in that direction, my charge will be making circular motion because of this force, I mean, in the subsequent moments. At this instant that my charge is moving with velocity v, I also go to a reference frame which moves in the same direction at constant velocity. At that instant, the magnetic force acting on my charge is 0. So there's no force acting on it. It will not accelerate. It will keep at rest, stay at rest. So it will be just staying over there with 0 velocity. Okay, in one reference frame, we said that it should be doing the circular motion. Then we said that in the other reference frame, it should be just moving like this. How is this possible? What are we missing? I will not discuss it in more detail. Okay? At least not until towards the end of the semester. This is just something to keep in mind. I mean, these arguments, well, not towards the end of the semester. Probably we will take just a couple of weeks to come back to this question. Now let's...
Sorry, what topic?
After induction. Now let's look at this example. Let's just assume we have a ring which has a uniform charge density. Furthermore, it is rotating. It has a mass m, radius r, and it has an angular velocity omega. So what is its magnetic moment? Well, there is a charge. There is a charge on this ring fixed. As the ring is rotating, the charges are moving. Well, moving charges is what we call the current. So due to this rotation, there is a current in this ring. But, well, if there is a current, there is an area. And current times the area is nothing but our magnetic moment. Well, what is the current? Let's start with that. We define the current as the amount of charge passing through a given point per second. Well, the current is uniform, so I can just imagine one full rotation of this Y ring. In one full rotation, the total charge that passes through, let's say, this point would be just the total charge of the ring, which is 2 pi r times lambda. This is the total charge that will pass through a chosen point in one period. Well, one period has a total, it lasts 2 pi over omega. This is the length of the period. In one full turn, the angle changes by 2 pi. So 2 pi's we can just cancel. This is omega r times lambda. This is the current running through my system. Or we could have just as well said the current density we had already discussed the current density should be the velocity times the charge density. So this is the velocity. This is the speed of the object. The current is also, since this is just an infinitesimal thin, the current is just the speed times the charge density. Now, we know the magnetic dipole moment. Its definition is, although we had derived it only for a rectangular wire, it is valid for any wire of arbitrary shape. So if you just, there is a current I running through this wire, which is omega r times lambda, times the total area of this wire is nothing but pi r squared. This is the magnitude of the magnetic dipole moment. What is the direction of this magnetic dipole moment? In the direction of omega, right? So it's just, this is the direction of rotation, this is the direction that my current is running, and we had defined the direction of the magnetic dipole moment as, using our right-hand rule, just curl your fingers in the direction of the current, your thumb points in the direction of the magnetic dipole moment. So this we can also write as omega vector pi lambda r cubed. Or let me also, instead of lambda, let me write it in terms of the total charge of my ring. Pi r cubed, lambda is the total charge divided by 2 pi r. So the magnetic dipole vector is nothing but the total charge divided by 2 r squared omega. Now let's see who remembers some mechanics. What is the angular momentum? Okay, r cross p, that is for a point charge. Here I don't have a point charge. It's I times omega. Well, this I is the moment of inertia, not the current. What is I for this ring? Mass times r squared. Well, that is for a point charge, but it's also valid for the ring because all the mass is at the same distance from the rotation axis. So this is equal to m times r squared omega. Or omega is equal to L over mr squared. So we can relate the magnetic dipole moment to the angular momentum. Mu, well, we have this constant qr squared over 2 times omega, which written in terms of the angular momentum, mr squared, r's cancel, q over 2m times the angular momentum. So any charge that has some angular momentum will have a magnetic dipole moment. Well, if an object has a magnetic dipole moment, it will feel a magnetic torque. And if the magnetic field is not uniform, it will feel a magnetic force acting on it. Now you were asking, who was asking, how come an object that is at rest, a magnet at rest, feels the magnetic force? Well, any object is made up of electrons and protons. Electrons and protons, they have angular momentum. Even at rest, they have an angular momentum. It's as if they are rotating around itself. They are spinning. Since they have an angular momentum, they have a magnetic moment. And since they have a magnetic moment, they will be feeling the force. Okay, then what makes the difference between, let's say, aluminum, which doesn't feel this force, and iron, which will feel this force? No. Well, you see, we have many electrons, and ordinarily they all have a magnetic dipole moment. They're all pointing in random directions. So if you have a material, if you sum them all up, the total magnetic moment of an ordinary material will be just 0. So they will not feel a net force. Some electrons will be attracted, some electrons will be repelled. The net force would be 0. But in a few materials, a few elements and many compounds, you can arrange that these magnetic dipole moments, they try to align in the same direction. Such materials will be attracted strongly. Now, we will study this in more detail later on when we study the magnetic properties of materials. But this is just to give a brief introduction, let's say.
So then, anything with electrons in it should have a magnetic field, right? Because you just said that even inside a magnetic field.
You see, if you just give me one electron, it will create a magnetic field. And it will also be influenced by the magnetic field. If you give me 2 electrons, and if you tell me that their angular momentum is in the same direction, then those 2 electrons will have a net magnetic dipole moment, and hence they will be influenced by the magnetic field. But the 2 electrons, their angular momentum can be pointing in opposite directions, in that case, the net force that the system will feel will be 0. It depends on how the angular momentum of the electrons are arranged in the material. Other questions? Now, in fact, basically, this is what we will be using also later on to describe the magnetic properties of materials. Just like in the electric case, we discussed the dielectrics. Now, also the magnetic materials have all the materials have certain magnetic properties. And so, although their magnetic properties will be one way or another way related to this expression over here. But that we will discuss later on. Now, there was one more example that we had discussed on Thursday. Now, by the way, I think it was a point of confusion for some of you. Now, when we call something a dipole, what we mean is not, in the case of the electric dipole, we had these 2 point charges. Now, a dipole is not necessarily this 2 point charge. We call something a dipole if it behaves like a vector. It has a direction. And in terms of the electric field lines enter in a given from an angle, and they leave from a different angle. So that is what we call an electric or a magnetic dipole. If you imagine the electric dipole also, and consider the electric field lines, we had the plus charge, the minus charge. So these were the electric field lines. For a faraway observer, that you will not be seeing this distance, they will just look like a point charge, point object, let's say not a charge. So you see that the electric field lines enter through this direction and they leave through the other direction. Just like in the case of a magnetic dipole. So a magnet is a magnetic dipole, and we had seen that the magnetic field lines just look like this. We have this point-like object, and the magnetic field lines leave from one side, and they enter through the other side. This is what we call this dipole. Both of these things have the same feature. So that's why we call both of them dipoles. Now, the other example that we had considered was this one. We had this wire. And then there was, the magnetic field. We had this conducting rod, which lied on, let's say, conducting wires, which is connected to our circuit. And we also said that if this rod is moving with a velocity v in this direction, on the average, the electrons in this rod will be moving with this velocity v. So they will feel a force in which direction? V cross B is upward. The force will be downward. So the electrons will be pushed downward. So this will be the flow of electrons. So there will be a current running through my system. So the electrons will be pushed downward. So they will go along this wire and come back to the other side. Well, you see, this is a battery. This is what the battery does. A battery just takes charges electrons from one terminal and gives electrons from the other terminal. So this whole system just acts like a battery. Let's say this is the length L. What is the magnitude of the force acting on the electrons? Q times V times P. This will be the magnitude. What is the total work done on the electrons by this force? QVB times L. What is doing this work, by the way? It's not the B. Basically, that's where the force will come from. You see, the electrons will not be moving straight down. As they move, they will start bending. And so they will hit the boundary of the metal and transfer their energy to the boundary of the metal. And hence, there will be either if there is no force acting on my system, this wire will slow down. Well, the EMF of a battery was nothing but the work done on a charge, per unit charge. So this is the EMF created by this moving rod. So then we can just treat this as a battery and even calculate what will be the current running through my system. We know the EMF source, we know the resistance of this resistor, etc. Now, before you go for a break, let me also go back to this example. Now we said that, okay, let's take this wire, and this is the current running through it. There will be a torque acting on it, which will be try to rotate it in this direction. And it will keep rotating until mu and B are in the same direction, because we said that the torque is mu cross B. Torque is mu cross B. If mu and B are in the same direction, there won't be any torque. So we started with this configuration. This is how the current is running. This is the magnetic dipole moment. So it will start rotating. There will be a torque acting on it until B field is in the same until the magnetic dipole moment is in the same direction. Now, what happens if you change the direction of the current? Mu will be reversed. So let's see. Suppose that we start with this configuration. It will rotate. When the mu field is in the same direction as the magnetic field, we change the direction of the current. So at this instant, mu is in that direction, but then we change the direction of the current, so now mu is in this direction. So, you see, it's moving. It is a velocity. So it will keep moving. But now the torque, we change the direction of the current, so we change the direction of the torque. So now magnetic dipole moment is in this direction. So it will again rotate to align itself with the magnetic field. And when it reaches this point, we change it once more. So as long as we keep changing the direction of the current, the moment that the magnetic field and magnetic dipole moment, they are aligned, this wire will keep rotating. So that is how we'll create an electric motor. The only critical thing is you have to make sure that you keep changing the direction of the current. Well, one way to do that. No, even with DC. I mean, you have electric motors working with batteries which provide DC. So basically what you do is you create such a system. This is your wire. Now here there is something which is connected to batteries. That's the DC. In that place, you basically have these what are called brushes. These are just conductors. This part is the part connected to the batteries, or to the battery. And then you have the wire. These wires, they say they will be pointing into the screen, into and out. This is A, this is B, this is A, this is B. So as your loop is rotating, as this wire is rotating, so just imagine you have this wire going to your circuit, to your loop over here, and coming back through this point. So as this is rotating, these points will be moving. And after half a rotation, well, the current, since A and B, they start connecting to the opposite terminals of the battery, the current automatically changes itself. So you don't have to do anything. You just create the system. Once you connect it to a battery, this system already automatically creates this changing direction of the current running through your loop. This loop over here, so you have an electric motor. Of course, in a real electric motor, you don't have just a single loop, you have many loops, and just to eliminate that, it just accelerates, slows down, accelerates, slows down. You create many loops at different angles, so you try to get this homogeneous torque acting on the system.
When the angle is 0, because of the sign 0 is 0, this is in equilibrium.
Okay.
But when the direction of the current is changed, the angle is 180,
80.
but again 0.
Well, there is only one such angle in which with one loop, it will stay at rest. And even a very small shake will change the angle from 0 to, let's say, 0.001 degrees, and that's enough to start the rotation. And furthermore, to avoid those problems, as I said, they don't have just a single wire, a single pair of brushes, but at least 2 of them, 2 or 3 of them, so that you don't have that problem at all. Okay, let's give a 10-minute break and we will continue.